Okay. To start out class today, we're going to continue our discussion of membrane potential. So what we're going to do is start by drawing a cell. I want you to draw on a chemical driving force pointing out of the cell. I want you to label where the ECDF would be, where the ICF would be. So remember what those mean from our divisions of total body water. And also put on the solute. So the chemicals dissolve in the water. You should be able to tell how many should be where based on that outward pointing chemical driving force. As you're drawing that, once you finish, if you have a couple seconds, think about what it might mean if you were looking at this cell and you saw that those solutes weren't following their chemical gradient. They weren't going the direction you expected based on their concentration. Why that might be. So as you're finishing that up or still thinking about this, let's draw together for a little bit. So I'm going to put on a cell here. So first, where am I going to label the ECF? Okay. It'll be out here, right? So that's our extracellular fluid, which means our intracellular fluid inside the cell, ICF. And we're going to be thinking about this chemical driving force pointing out. So we're going to be pointing from the ICF to the ECF. I'll go ahead and label that as well. So that's our chemical driving force. And then we want to put on our solutes to make sure we understand where that chemical driving force is from. So when we say solutes, we mean whatever particle it is we're tracking. Take a stamp and put some stars. Okay. So which of these is going to have a higher concentration of solutes, the ICF or the ECF? The ICF, yeah, great. I'm going to put a bunch of solutes inside, high concentration, low concentration out there. That is our situation that we've described. So as we're moving forward, we're going to be thinking about times when we may or may not follow that direction. We may or may not follow that chemical driving force. So anybody want to volunteer some reasons that we might not have our solute going from inside the cell to outside of the cell in this situation? What could we be thinking about?
It's not flowing down.
Mm-hmm.
I was gonna ask, but
Yeah, go for it.
so when there's like the air will flow, and also so when it flows through the gradient, but it also flows out of the gradient, what like when you focus on both of them like that, you know what I mean? Or is it just like where the solids go, most of the solids?
I think I know what you're asking, so I'm going to answer what I think you're asking, and then tell me if I understood you right. So when we were talking on whatever day that was, Wednesday, where we saw the two areas on our figure.
Yeah.
Yeah, so that actually does kind of get to this question that I'm asking, right? So all we have drawn on here is the chemical driving force. So a reason we might have solutes not going in that direction is the electrical driving force, which is a separate force on the particles, right? So if we had a really large electrical driving force, right, pointing the opposite direction, let's make it longer so we can see it's bigger, right? If we were talking about a charged particle and our electrical driving force was really strong because of our charges, then we might see the solutes following that arrow, right? So they're going to go with whichever arrow is bigger. Basically, whichever force is greater in magnitude, whichever force is stronger.
So they're not also tied into like the question.
Exactly. Yeah, so that's one of our possible reasons, absolutely. Yeah, so if that electrical driving force is larger, or if it's the same size, if they're the same size, that solute isn't going to move, then that might be a reason we wouldn't see our solute following the chemical driving force. Anybody think of any other answers why we might not see this happen? Think about our membranes. Remember when we talked about our membranes as being selectively permeable? So in order to have solutes flow, our membrane has to be permeable to that solute. So when we're thinking about things with electrical charges, for example, we would need to have membrane proteins that make that membrane permeable to that molecule. That's just a kind of touch back on the membrane topic. So we are going to go through this some more. So we talked last time about chemical driving forces with these concentrations. So that's what we drew in that first picture. We talked a little bit about electrical driving forces having to do with the charges on cations and anions and how that relates to the charge of a cell. Okay. So now we're going to be adding them together to get our electrochemical driving force, which is going to be the total force which actually controls the movement. So before we were basically talking about two pieces that are pushing and pulling the same particle. And now we're figuring out where that particle is actually going. So if we have a cell, okay, let's say this is our cell. We have the chemical and the electrical force going in the same direction. So let's say our CDF is pointing out. CDF, our chemical driving force. And our electrical driving force is also pointing out. So from the intracellular fluid to the extracellular fluid. Color. Then we have a pretty easy situation because they're both pointing the same direction. There's no conflict for our particle, right? Its charge wants it to go one direction. The chemical concentrations want it to go that same direction. So our total force is going to be big because we add these together. But we can easily tell that it should be going out, right? Let's make it say twice as long. So our total force here, which is the one we ultimately care about, if we looked at the cell, those particles are going to follow that electrochemical driving force. Our ECDF is going to point out. So its magnitude, how big it is going to be that sum of the chemical force and the electrical force. We won't be calculating that in math terms, but we want to be able to compare sizes. This is bigger, this is smaller. Does this setup make sense here? Okay. And the difference between these forces. Cool. Okay. So our problem comes in when we have these forces in opposite directions, right? So when we have them going opposite, take our cell again. Okay. So our chemical driving force, I'm going to keep it orange. Our chemical driving force pointing out, say. Now let's say our electrical driving force is going to point inward. Make it a little smaller. So in this case, where do you think we would draw that red arrow, that some electrochemical driving force? Is it going to go in or is it going to go out? Yeah, in this case, it always just goes with the bigger one. So that's what we mean when we say that we're summing them. So we're going to have whatever's left over, right? So it's going to be smaller than the orange arrow because we're basically subtracting this EDF, the green one, from the orange one, the CDF, but it's going to point out. Okay. So if these forces are in opposite directions, we're going to go with whichever force is bigger, whichever force is stronger, whichever force has the greater magnitude. So that may be the CDF or it may be the EDF. If I drew this green arrow really long and that orange one really short, it would go into the cell. We're just trying to figure out which one is bigger. Okay. So this is a rephrasing of our question from before, right? So our membrane has to be permeable to the particle for it to move across the membrane at all in any direction. But if we have a chemical gradient, it's not going to be transported unless either the electrical gradient goes in the same direction, so there is no conflict, or that electrical force is smaller. If the electrical force is bigger, goes with the electrical force. And if they are in the same, if they are the same magnitude, so if we had two arrows pointing in opposite directions, but they're the exact same size, all right? Let's draw on the situation. So our chemical driving force, let's point it out. Let's find our electrical driving force in. If these arrows are the same size, these forces have the same magnitude, there is no movement at all, right? So we're going to see on net, no ECDF, our ECDF would be 0. Now we're going to be talking about something called the equilibrium potential. This is a value you'll get for like specific ions that is describing what charge inside the cell, what membrane potential leads to this situation. Right, so we said before that our cells are going to have some membrane potential, which we wrote Vm. Right, I was telling you that the most common one we'll talk about is negative 70 millivolts. Right, but this can change. And when it changes, that's going to change the magnitude of that electrical driving force, because the magnitude of the electrical driving force is dependent on the charge on a particle and that charge on the cell. So when we get to the equilibrium potential, essentially what it's going to tell us is when the cell is at this equilibrium where these two forces are going to be equal for any given ion. So just another example. So here what we are seeing is a way we might set up a problem, right? So this is telling us that our cell
Its membrane potential in this case is positive 50. All right, so that is our membrane potential. And we're given the concentration of sodium outside the cell and inside the cell. So think about our three forces and what they're going to look like here. So first, looking at those concentrations, what's going to happen with the chemical driving force? Is there going to be a chemical driving force? No, we have equal concentrations here, right? 30 and 30. So we're at equilibrium. So we're not even going to bother putting on a CDF, right? CDF equals 0. So this means that to find that movement of that sodium ion, we need to figure out the electrical driving force, because since the CDF is 0, the EDF is going to be larger, right? It's going to be something. It's not going to be 0 because we have these charges. Okay. So which direction is that EDF going to point? Which direction, looking at these charges on the cell and on that ion, which direction is sodium going to want to move? It's going to go towards the positive charge or away from the positive charge inside the cell. Yeah, it's going to go away from it, right? So positive charges repel each other, like charges repel each other. So if this is all the information we have, they're basically bouncing off of each other, right? Without any other information. It's going to point out. So our overall movement is going to be out of the cell here.
So how do you know that it's the EDF that's going to move and not the CDF?
So this situation, we first looked at the CDF, right? So we looked at the CDF to find those chemical concentrations. And we thought it had like the same amount of sodium inside the cell and outside the cell. So in this case, we didn't have any chemical force. So that chemistry, that concentration isn't pushing or pulling on it. So the only thing pushing or pulling that ion is the electrical driving force. Does that make sense?
So then with the EDF, you include the 50 too, so that's why it's.
Yeah, we basically have both of these forces acting together, but in this case, there's no chemical driving force.
Okay.
Yeah. So how we figure out which one we're following is we figure out which is bigger, but 0 is not bigger than anything here because we're thinking magnitude. So we'll take another example. Think about the chemical driving force, the electrical driving force. Then we might think about that overall force. Trying to figure out whether the potassium is moving into the cell or out of the cell. We're going to try to figure out that electrical chemical driving force. So the first step of that is figuring out the directions for each piece of it. So when we're looking at the chemical driving force, which direction are we going to be pointing here? Yeah, perfect. So we have a high concentration of potassium inside the cell. We have a low concentration of potassium outside the cell. So we move high to low. Chemical driving force wants us to go out. So next, we're going to deal with the charges. We're going to look at that electrical driving force. The potassium is a cation, it's a positive ion, and our membrane potential is positive 60. So what's going to happen with those two positive charges? I'm going to want to go into the cell or out of the cell. Yeah, it's the same setup as with the sodium, right? So positive repels positive. So it also points out. So in this case, neither of these forces are pointing in. So we know that the ECDF has to point out. So that potassium is going to move out of the cell. Mhm. You're not going to have to calculate that. You will be given that membrane potential if it's relevant. So when we are talking about action potentials in neurons, that's where we're really going to be paying attention. Mhm. Yeah. I mean, it may be written in words, but this is like what you should be thinking and like drawing on your scratch paper for yourself. Yeah. Because when we talk about how nerve signals, we're going to see that that charge on the cell changes, basically. That's kind of why we're leading up to that. So finally, one more, and then we'll get back to the slides you have prepared in front of you. So we're going to track a chloride ion. So we're going to track a negative ion, an anion now. Okay. So we're going to start with that chemical driving force. We're comparing our concentrations here and here. All right. So hopefully we all saw that we have a high force, or sorry, a high concentration outside the cell versus a lower inside the cell. Okay. Which means that our chemical driving force points inward. And in this situation, when we're looking at that electrical driving force, we have a charge on chloride ions, but we see here that our membrane potential is 0, which means that chloride ion, there's no push or pull on it at all because we don't have charges interacting. So in this example, we have no electrical driving force, which means that our total electrochemical driving force is going to point inward along with that CDF. In this case, our chemical driving force was stronger than our non-existent electrical driving force. So that ECDF follows the CDF. So for these examples that we've just went through, because the way the directions align, we could do it just by looking at those concentrations and the charge inside the cell. But as we build forward and see slightly more complicated situations, we're going to have to think about our equilibrium potential, which is going to be a topic we'll see in a second. Our equilibrium potential kind of sums this all up for us. It can kind of describe this situation. So we're looking at our chemical driving forces, and we're looking at our electrical driving forces, and we want to know what happens if they're going in opposite directions. And ultimately, when they're going in opposite directions, if the electrical driving force is bigger, we go along with the electrical driving force. The chemical driving force is bigger, we go along with the chemical driving force. But if they're exactly the same, we're at equilibrium and we see no movement. So the equilibrium potential, equilibrium, it tells us what charge is going to be inside the cell when this happens, right? Like what is the number for our membrane potential where we see no movement of that ion? So it's always described, or it's always written down as E something, right? So E for equilibrium potential. We're going to have a different one for each ion because this is summing together chemical driving forces, which have to do with the concentration of a specific substance. So when we're thinking about the chemical driving force of potassium in this example, we're just looking at the concentration of potassium inside and outside the cell. We don't care about the concentration of sodium. We don't care about the concentration of glucose. We're just tracking potassium. So that means that when we look at this sum together, we need to be specific. So we'll have an equilibrium potential for potassium specifically. When we look at electrical driving forces, because that's a summary of just like positive and negative, if we had a lot of sodium somewhere, that actually would change this membrane potential. That's part of it, right? That's the sum of all the cations and anions. So that electrical driving force is going to be compared to the chemical driving force. So if you were just talking about electrical driving force, all of the different ions affect it. But when we think about equilibrium potential, because we track a particle separately on its own, when we're thinking about that chemical driving force, our equilibrium potential has to be specific. So in this case, we see our equilibrium potential for potassium is negative 94. And that means that if the cell is at anything other than negative 94 millivolts, potassium is going to move. And it's going to move in whatever direction it takes to get that cell to negative 94. Once it's at negative 94, it stops. It doesn't move on net into or out of the cell. So we want to think about that equilibrium potential as we're trying to get to the stable point for that ion. And at the stable point, our chemical driving force and our electrical driving force are equal to each other. So that's our setup. I'm just drawing this out, right? If our membrane potential is the same as our equilibrium potential, we might also say that the force is 0, right? So in this case, our chemical driving force and our electrical driving force are the same. So if we were trying to figure out, as we were on those previous examples, if we wanted to know what the ECDF was, right? There wouldn't be one, right? It equals 0 because they are equivalent but opposite in direction. Same magnitude, opposite direction. So if we add them together or subtract them, we're getting a 0. Okay. And this X bit, this is telling you, right, that you have an equilibrium potential for potassium, but we'd have a separate equilibrium potential with a separate value, a different charge for sodium. We'd have a separate equilibrium potential for chloride and so on. So not all of these ions are going to want the cell to be at negative 94. They're always going to, or each of them is going to have their own specific charge that they're trying to get the cell to. So when we're thinking about this, your book likes to talk about it, and probably your SI leaders will talk about it this way as well, as when the membrane potential is weaker than the equilibrium potential versus stronger, right? But the way I fundamentally think about it is, right, like we're just trying to get to this value, right? So in this case, we're tracking potassium. That's a positive ion. Our cell is starting at -70. So in order to get down from -70 to -94, we need positive charges to leave the cell, right? As they leave, they make that cell more and more and more negative. So our electrochemical driving force is going to point outward, telling us that those positive charges want to leave the cell until we hit -94. So that's what it means that that membrane potential is weaker than that equilibrium potential. On the opposite side, this is a membrane potential that is stronger than the equilibrium potential, right? So we see that this magnitude, -100, is greater than this magnitude, -94. But we have potassium that still wants to get to that same value. So potassium wants to bring to the cell to -94. Our cell is at -100. Potassium is a positively charged ion. So we have to add positive charges into the cell to get from -100 to -94. So our total electrochemical driving force is going to be inward into the cell. So the way that I like to think about that equilibrium potential is just we're trying to get to that value into the cell or out of the cell, but we can also think about it as these forces being weaker or stronger. In this case, this lower value is weaker than that stronger.
Yeah, where you going?
That you can't have it go towards equilibrium.
Yeah.
It's always going to want to go towards its equilibrium point. It's not always going to make it there, if that makes sense. So like the potassium is going to be sometimes be like fighting the sodium equilibrium potential. So we're not going to see the cell often get down to the equilibrium potential for one specific ion, but that's always going to be the direction that that ion wants to go. That's like, just definitionally, that's what it is for that ion. Yeah.
For equilibrium, that potential that will use the electrochemical driving force is also for kind of like that.
The equilibrium potential is for the electrochemical driving force, so the two of them added together. So part of why this happens is that we have different concentrations of different things inside and outside the cell. So all of that is kind of factored into these equilibrium potentials. So these are some questions that will hopefully be somewhat clear in your mind after looking through this and looking through the same sections in the textbook. And what I want to point out, because we're actually going into passive and active transport next, so this is what we're jumping back to. So we want to remember, right, passive transport is our whatever our favorable direction is, whatever doesn't require energy. Active is going to require energy. So now that we know about this new summative force, this electrochemical driving force, before, when we thought about passive and active transport, you were probably just tracing chemical driving forces, because that's the easiest example to start out with, easier than adding the two together. But now when we're talking about passive and active transport on ions, we're actually going to have to think about that whole electrochemical driving force. So for uncharged particles like glucose, you can still just think about we're going from high to low concentration. But now to figure out which direction would be passive versus which would be active, we're going to have to think about overall summing together the chemical driving force and the electrical driving force. Which direction does this ion want to go? We only have to sum those things together when we're thinking about ions that have charges. There's no charge. We can just think about it without thinking about an electrical driving force. Okay. One more question for us. This is a slightly differently phrased question. So this is about our equilibrium potential. So sodium has an equilibrium potential of positive 60, different than our potassium equilibrium potential. We want to think about where that electrochemical driving force would go if our membrane potential, so like our starting point for the cell, is negative 70 millivolts. If the situation happens to already be obvious to you, start to think about how you can then backsolve to think about that electrical driving force and possibly even also the chemical driving force. Adding on our equilibrium potential for sodium specifically. So we know that sodium wants the cell to come to positive 60. Okay. So the electrochemical driving force is our summative force that actually controls which direction sodium goes. So to get to positive 60, is sodium going to go into the cell or out of the cell? Yeah, it's going to go into the cell. We have to make that way more positive. We have to go up 70 and then we have to go up another 60 more. Okay. So our total force, our ECDF, we can figure out looking just at those two numbers, just at the membrane potential and that equilibrium potential for sodium. We actually don't have to add anything together to figure out that total force if we're given both of these. However, we want to know those other forces, we can start to try to back solve, right? So we might draw on, right? I like to do the electrical driving force next. For the electrical driving force, we need to know two things, right? We need to know the charge on the cell, and we need to know the charge on the particle, right? So sodium, positive charge, our starting membrane potential, negative charge. So which direction is our EDF? It's into the cell, right? So those opposite charges attract each other, right? So our EDF goes into the cell. So this means in this situation that ECDF is following the EDF, right? So it's going the same direction as that electrochemical driving force, right? So we know that either this is stronger than the CDF Or maybe they're both pointing the same direction, but we know that this ECDF is absolutely going the same direction as that EDF, right? So if we had the opposite situation where that equilibrium potential told us we were going one direction, but then you look at that charge on the cell versus the charge on our ion and they're going opposite, then you would know that that chemical driving force has to be really strong in order to create that situation. Oh, sorry guys, I pulled out a lot of practice problems. I think it's worth practicing this a fair bit to just crystallize it in your head. Yeah. Okay. But first, just a reminder, so to figure out moving into or out of the cell, which of our three forces are we thinking about? Which one are we looking for? Yeah, the total, right? The electrochemical driving force. So we're looking for the direction of the electrochemical driving force. So we can see, we know a couple facts, right? We know chloride ions are negative, they're anions, right? So they're carrying a negative charge. We know the cell is at negative 66 millivolts. That's its membrane potential. We know that our equilibrium potential for chloride ions, ECl, is negative 61. So how could we get negative 66 to negative 61 by moving chloride ions? You're going to move them into the cell or out of the cell. Yeah, exactly. So imagine, right, that every time we take a negative charge out, right, we become a little more positive, right? So you move a chloride ion out, you get to negative 65, you move another chloride ion out, you get to negative 64, right? Not true that it's one for one like that, but that is the direction these go. So we know that chloride ions are going to move out of the cell until we get the cell up to negative 61. We might want to look at some other forces and just think about them. So our other information that we have, right? We already know chloride ions are negative. We know the cell is negative, right? So we know that chloride is going to get bounced out of that cell. They're repelling each other, that same negative charge. So we know our EDF would point outward in this situation. And we've been given information about that CDF, right? So we have our concentration of chloride ions outside the cell versus inside the cell. So we can see that we have high outside the cell, we have low inside the cell. So we can see that the CDF actually points inward, but we know it has to be smaller because that ECDF is pointing out, right? So from this information, we could actually back solve and figure out the magnitude and direction of all of these forces. Questions about how I did that there? So that's how we kind of want to be thinking about these forces. Moving out. Okay, we're actually going to stop here and we'll start out with this next time because I think this is enough of a big important topic for you to think about.
Can I ask you a question?
Yeah, let me stop recording.